In this example video, we're going to cover these two problems. We are going to graph the polar equation r equals theta, and we are also going to graph the polar equation r equals 4 times cosine of theta. Let's work on these one at a time. Starting here with the graph of the polar equation r equals theta. What we're going to demonstrate here is the typical way to graph most equations in polar coordinate systems. And the way to do that is simply to make a t-table of values. Note that our independent variable here, theta, is the value that we're going to consider as the value that we plug in. And we will get r back as our independent variable in a very similar fashion as if this was x and y. For this case, the t-table is going to be relatively simplistic because when we have r equals theta, that means no matter what I plug in for theta, I'm going to get the same value back for r. So, for example, if I plug in 0 radians for theta, I'm going to get 0 back for r. If I plug in pi over 2 radians for theta, I'm going to get pi over 2 back for r. However, it is familiar to graph angle measures as radians like this, but a radius of pi over 2 is a little bit less familiar. In this case, then, I'm going to round my values for the radius to decimal places. Pi over 2 is approximately 1.6. If I plug in pi, I will get pi back in return, which is approximately 3.1. If I plug in 3 pi over 2, that gives me 3 pi over 2 back in return, which is approximately 4.7. And then if I plug in 2 pi, that gives me 2 pi back in return, or approximately 6.3. Using these values, we can graph this function. Start off with theta of 0, r of 0. That would refer to the pole, or at least that's one representation of the pole, but that's where we're starting. Then we have pi halves as our angle measure, and 1.6 as our radius. To graph a point like this, I recommend thinking about this as face towards pi halves, and then walk a distance of 1.6. Well, face pi halves, which is akin to the y-axis on the Cartesian plane. So face vertically, and then walk a distance of about 1.6. Maybe about 1.6 is roughly here. That's my first point, that's my second point. My third point would be if I face towards pi, walk a distance of 3.1 in that direction. Pi would mean that I'm facing towards the negative x-axis on the Cartesian plane. I'm facing this direction, and I'm walking forward a distance of 3.1. This throws some people off, but this means that we're going to be 1, 2, 3, and a little bit further in the direction of pi. Some people may be tempted to put that point over here, but remember that you're always walking forward in the direction that you are facing as long as your radius is positive. We would end up over at this point if we had a negative radius when facing towards pi. Same will apply to our fourth point. 3 pi halves, that means face towards 3 pi halves and walk a distance of 4.7. So that would be 1, 2, 3, 4, almost to 5. So this would be my fourth point here. The last point I have, I may not be able to graph. It's a little bit off the graph here. 2 pi and 6.3 means face towards 2 pi. and walk a distance of 6.3, which would put me, if 6 is around here, 6.3 is a little bit past that. That's my 5th point. When I connect these dots in order to make my graph, the way that polar coordinates works is all about rotation. So I'm not going to connect them to make it look like this. I'm not going to do that. Instead, consider that as we rotate counterclockwise, which is what we're doing when we're plugging in larger angle measures, my radius is getting progressively larger. Which means that we're going to rotate out from our first point to the second one. And then we're going to continue to rotate out counterclockwise to get to that third point. And then continue to rotate to the next point. And then to the next. And beyond. What we have now graphed is the equation r equals theta, which forms a spiral. Let's look at the other example of r equals 4 cosine of theta. With r equals 4 cosine of theta, we're going to plug in values of theta in order to get values of r. This one's a little bit more interesting than the previous case, because we actually have a function to work with. So for values of theta, let's start by plugging in 0. If I do that, I will have 4 cosine of 0. Cosine of 0 is 1, so that's 4 times 1, which equals 4. I can continue to plug in values as I so please, but in this case, I'm going to choose to plug in pi over 4 next. If I do so, I will get 4 cosine of pi over 4. Cosine of pi over 4 is positive square root of 2 over 2. And 4 times square root of 2 over 2 is approximately 2 square root of 2, or if you approximate that, about 2.8. I will then plug in pi over 2. 4 cosine of pi over 2. That would be 4 times cosine of pi over 2, which is 0, meaning that this comes out as 0. Now, I chose to plug in pi over 4 here to get some more points instead of just doing 0, pi halves, pi, and the remainder of values after that. We could have chosen to do any other values. For example, if you wanted to do pi over 6 or pi over 3, then that's perfectly fine. Do whatever values you need in order for you to understand how to create the graph. That is always the best consideration. If you don't know what is happening between any 2 points, try graphing another point in between using another angle measure. That might help you connect the dots. If I continue forward with this pattern though, I'm also going to plug in 3 pi over 4 as well as pi. If I plug in 3 pi over 4 here, I will get 4 times negative square root of 2 over 2, which is approximately negative 2.8. And if I plug in pi, I will get 4 times cosine of pi is negative 1, which will give me negative 4. This should probably be enough to graph what I'm going to be creating here, so let's see what this does. First, theta is 0, r is 4. That means face towards 0 radians, which means we're facing this way, and we're walking a distance of 4 in that direction. Puts us here. This is our first point. The next one I have is pi over 4 with 2.8. That means face towards pi fourths, which is halfway through what we could imagine as quadrant 1 of the Cartesian plane. And I'm going to walk a distance of 2.8 in that direction. So that would put me roughly here if I face towards that direction. That would be my second point. My third point I have is pi halves with 0. That means face towards pi halves, face vertically, and walk a distance of 0. If you are walking a distance of 0, that means you're not moving, means you're at the pole. That's our third point. Next, we have 3 pi over 4 and negative 2.8. So that means face towards 3 pi over 4. So we are now currently facing towards 3 pi over 4, which you could imagine in the second quadrant of the unit circle. Our radius, though, is negative 2.8, which means even though we're facing towards 3 pi fourths, we're going to walk backwards, which is what negative radius means. We're going to walk backwards a distance of about 2.8, which would put us about here. That would be my fourth point. The last one we have is pi, the radius of negative 4. That means face towards pi, which is back this direction. And when facing towards that direction, walk backwards a distance of 3, or 4 rather. If I face towards pi, walk backwards 4, that puts us actually right back to where we started. So, as I connect point 1 to point 2, note that as I rotate counterclockwise, my radius is getting smaller. So I should have a curve that kind of approaches towards the pole, implying my radius is getting smaller. And as I rotate towards pi halves, my radius gets even smaller, eventually towards 0. As I continue to rotate counterclockwise, my radius gets increasingly negative, which is going to push us back towards point 4 here. And then towards pi, my radius gets even more negative until I get to this point back to where I started. This equation, r equals 4 cosine of theta, is technically the equation for a circle centered on the Cartesian plane, point x is 2, y is 0.